All right, couple of things. One thing that was just brought to my attention, and I just assumed this was people were doing this, but apparently not everybody knows about it. One of the advantages of me having my PowerPoints online is so that you can actually, one way to use them is to print them out, 6 to a page, 3 to a page, and then you take notes on the PowerPoints. That way you don't crazily try to write everything I say, or you have it open. I just assumed that this was common knowledge. Apparently it's not. That's an advantage. That way you don't have to keep going back and forth, right? You don't know what you don't know. So I don't want to insult anybody's intelligence. If you didn't know that, now you know. Okay? It's useful. Okay. Another thing. I have 4 pieces of candy here. Right? So for the first 4 people that ask me questions today, you're going to get a piece of candy of your choosing. It's as simple as that. You ask a question, you get a piece of candy. Just a thought. I have Pops, Smarties. I got all kinds of garbage in my office. You can't even imagine. So nobody stops by anymore, so now I got to give it away a different way. Candy. So if you have one running through your head, it might be a good time to ask. Okay, we're going to continue with, so reminder, quiz on Friday, right? So you know, quiz on Friday will be from wherever we left off from the last quiz, going forward, both lectures and reading. All right, we're going to talk a little bit about equations. So this is in your book, so I'm just going to put it up here. This isn't in the PowerPoints. I didn't realize it until we started going through them. So I'm going to have to write this up. So the one equation, and I should have written this down so I don't have to keep going back and forth. Let me make sure I know theirs. It's ion. And I'll tell you in a minute why. Okay, so let's do this one first. There's 4 forms of this. Okay. This is the Nernst equation. All right? So we talked about this is the equation. If you want to know the contribution of an ion to the resting membrane potential, if only that ion existed. The Nernst equation is a theoretical construct. Right? It is a theoretical construct. This does not happen in nature. Does everybody understand that? In other words, this is something you as a scientist would do in a lab. Could you do this? You could do this experiment, right? But it doesn't happen naturally. Okay, so what does this say? It says that the E, which is the electrical potential of whatever ion you want to figure out, okay, is equal to 61 over, and this is my Z, so I'm sorry. Z. Not a 2. My handwriting's atrocious. 61 over Z multiplied by the log of the concentration of that ion outside and inside the cell. Now, the reason I have to keep looking back is that there's 4 versions of this equation, right? And the big boy and the big girl version of this equation has Faraday's constant and temperature and a bunch of other things in it. They sort of loop this in and make it 61 because it's roughly what it comes out to be anyway. So if you're not a chemist or a physicist, you really don't need to do all that other stuff. Okay, so this is the equation. So for instance, an example, I'll give you just the example that they do in the book, is they have one with sodium, right? So sodium has a +1 charge. The Z stands for the valence. Right? You can think about it in lots of ways, but you just think about it as the charge. Right? If there's a +1 charge, the valence is a +1. If there's a -1 charge, the valence is a -1. -2, it'll be -2, right? So 61 over +1, right? And then you have to do the logarithm of concentration outside and inside the cell. Now, what they use here is they use 145 and 14. 15? Let's see what they use. Let's make sure. 15. Our numbers are slightly different. Okay? So, as a reminder of what a logarithm is, all a logarithm really is the inverse operation of an exponent. Right? Exponents are really, really large numbers, right? When you go say something goes exponential. And so when you have a scale, for instance, like pH, where the difference between a pH of 0 or 14 is immense, huge. You can't put that on a graph. If you wanted to graph it, you couldn't do it. So you have to convert it into a form that allows you to take a really large number and a really small number and then graph them together. The only way to do that is to do the reverse function, which is a logarithm. It takes really, really big numbers and it makes them manageable. That's what a log is, for the long and the short of it, okay? So when you end up doing this, right, what you end up getting is a positive 60 millivolts. You can do the math and figure it out. It works out, okay? Now, what the heck does that mean? That means that if I had a cell, an artificial environment, right? Here's my bath, and I have a cell. Okay, I've created the environment, I've created the cell. And this is a semi-permeable membrane, and the only thing that's out here is sodium. And I also have a voltmeter. Okay. Remember, this is the reference side. And this is what I'm actually trying to measure. The voltmeter in here, right? With this being a negative, this being 0, and this being positive. And I start this, I've created this, right? I created the cell, I put it in a bath. The only thing that's in this bath is water and sodium. Okay, maybe there's sodium chloride in there too. It doesn't matter. There's sodium chloride in there. But this membrane is only permeable to sodium. The water, water goes in and out. Okay? If that was true, what would the resting membrane potential of this cell be? If only that ion was permeable. Now, typically it's what? What was the range I said for most cells? In this case, we're talking about a neuron. So we're talking about a neuron. What's the range? I said most cells have a resting membrane potential range of what? -40 to -90. Okay? So if I measured this in a normal cell, it'd be somewhere in that range. But if I do it with sodium, what I end up getting here is it's positive, and that number is going to be plus 60 millivolts. So this is the Nernst potential or the equilibrium potential. It means the same thing. I can call it either one. I'm saying the same thing. And what it's saying is that if this semi-permeable membrane that's only permeable to sodium, when sodium equilibrates, the voltage I'm going to read here is going to be positive 60 inside that cell. Now that's a lot different than the resting membrane potential of a neuron, right? Because we just said it's from -40 to -90 is normal, and we're saying that this would be positive 60. Okay? You can do the same thing. So they do the same thing in the book, and they do the same thing for, and I'm not going to do the equation, and it's for potassium, and you end up getting a -90 millivolts. So you do that same experiment with potassium, and all of a sudden you get -90. Okay. Trick question, maybe. Thinking question. If that's true, and I didn't make any of this up, this stuff is in your book, right? I just pulled it out of the book. If that's true, which one of these ions has the greatest impact on the resting membrane potential or on a muscle cell or a neuron? Potassium or sodium? That's the easy question. The second question is why? Okay. So which one of these ions has the greatest impact on the resting membrane potential of a neuron? Let's just use a neuron because we're doing the nervous system. Is it sodium or is it potassium? You got to think about Alex, what kind of information do you already know that I told you?
So the resting membrane potential is the range from -40 to -90.
Right. So that's the range.
So I would say that sodium, because it's +60 instead of...
You're saying that sodium has the greatest impact on creating that membrane potential.
I guess, yeah, because
Okay, go ahead.
potassium is in that negative range where sodium is positive range, so that's a greater difference. But
It's a greater difference.
yeah, potassium is within that range. Sodium.
Let me ask you another question. So are you thinking about this in terms of which one will have the greatest effect on changing the membrane potential?
Yeah.
Yes. So that is true. So Alex is actually answering a different question. Okay? But what I'm asking is which one actually has the greatest contribution on creating that -40 to -90? Not which one has the greatest effect on changing it. Right? That -40 to -90, if you had to pick one ion that has the greatest effect on creating that, and I'm only giving you a choice of two, which one would it be? Would you have the same answer or is it a different answer?
I would say that potassium.
It's potassium. That's right. And so, if you had a cell that was only permeable to potassium, the resting membrane potential of that cell would be -90 millivolts, which is in the range. Now, what Alex was answering is, if I wanted to change that, if I wanted to actually have an activated neuron that would fire an action potential, which one could actually make the biggest impact? And then sodium, absolutely. Yep, go ahead.
Yeah, the reason I said that is you said, like, has the greatest effect on me.
Yeah, and I was not very clear, right? So my language wasn't very good. So what I'm asking is, which one creates that, has the greatest effect on creating that? So, very, very good. Okay. So, but the cell, the resting membrane potential isn't usually -90. It can be. It's usually somewhere in between. And so most neurons you'll actually see probably fall in the range of 60 millivolts. Okay. That's the real. Why? So if this one has the greatest impact, then why do most of the cells are really about an average. We're going to call this the average neuron. Is -60. Why do you think that might be? Yeah. What's that? When it's at rest. Yes, when it's not doing anything, most of them are at -60. Why? The gates are closed, but are all of the gates closed? No. Okay, so that's part of it. So potassium, there are what are called leaky potassium channels. They're always leaky, but there aren't a lot of them. They allow potassium to leak. But the sodium channels are closed. Okay, but my question is, why isn't the resting membrane potential of an average cell either -90 or +60? Why is it -60? You have to understand. Yeah.
It's a combination of both -90 and +60, so it's going to be somewhere in between.
Yeah, and are those the only two that matter?
No, there's also others.
There are also others. Yeah, it's all of them together. If you take all of the charges inside and outside and you put them all together and you say, okay, you're positive, you go there, you're positive, you go there, and you start doing this, right? Ultimately, what you would find is that you have, with channels open and a bunch of stuff, is that here's the sweet spot. That's where they are when they don't do anything. Yeah.
Is the -90, that including penetrating substances?
Yes. No, it doesn't include penetrating substances. Well, I guess it doesn't include the ones that we talk about, but it does include like fats, which don't have a charge. What do you want? You can always donate it. All right. I'm not training like dogs, by the way. I was watching the Westminster Dog Show last night, and I thought, well, if I do this, they may think we're like they're dogs. You're not. I don't think you are. It tends to work. I need to give away my candy, is what it is. I need a reason. Okay. Yes, it's all of them together. So does this equation mathematically accurately describe the resting membrane potential on its own? Does this equation on its own, the Nernst equation, the equilibrium equation, does it mathematically describe the resting membrane potential accurately? It doesn't. It can't. It can't ever do it, right? Because of what Michael just said. It's because it's the contribution of every ion that creates the resting membrane potential, meaning this value. And knowing the ranges of this one and this one sort of says, well, it's going to be somewhere between, theoretically, it's somewhere between negative 90 and positive 60. Realistically, we've never measured it less than, negative 40 or negative 90, right? So, but because of this, it could be theoretically, right? Okay. Is everybody okay with that? Okay. Good. Next one, real quick. So now if you understand that, then you could say, well, all right, so I get the whole ion thing. So you could do this for magnesium, you could do this for chloride. You just need to know values. You could do it for bicarbonate. Anything, you pick an ion, it doesn't matter. You can calculate this for every one of them. If you have the information, it's not that hard to do. Okay, so now, we'll stay here. So now I will write this one out. All right, so this one, all right, so 61 multiplied by the log of, all right, big P stands for permeability. KO stands for the concentration of potassium outside the cell. All right. We'll get to what this thing is called in a second. And this is Ki, right? And we're going to add it to sodium. Sodium inside the cell. And then because it's the ion changes to a negative, we have to switch them around, and it's going to be chloride inside the cell over chloride outside the cell. So that equation is called the Goldman-Hodgkin cat, GHK. So that says that the resting membrane potential, notice how it's not E, because E stands for equilibrium potential. V stands for the resting membrane potential. Of a cell, in this case neurons, is 61. Again, the 61 takes into consideration Faraday's constant, temperature, right? A bunch of other constants, which we're not going to worry about. Multiplied by the log, and here you ultimately have the permeability of potassium to the membrane. So how permeable is your membrane to potassium? Okay, both inside and outside. And then you have the concentration of that ion outside the cell and inside. Do the same thing for sodium, outside, inside. You do the same thing for chloride, inside, outside. It's reversed because of the charge. You add them all together, you take the logs of this, you multiply it by 61, and you're going to get a number, right, that's somewhere between negative 40 and negative 90 millivolts as your resting membrane potential. Now, this only has 3 ions. Why is it that it only has 3 ions? I just said magnesium, bicarbonate, penetrating substances, they're technically part of it, but since they don't have a charge, they really don't do anything, right? Like fats and steroids. Why do I only need these 3? What's special about these? So the first question is it 100% accurate? It's not. So if I really, really wanted the true accuracy, right, at a physics level, right, I would have to then take all of the ions present and put them through the same rigor, right? But at the level that we're at, Alex, question.
No, I was just going to
Yeah, go ahead.
I guess would it be like those ions or those that are at highest concentration that contribute most to the member?
The highest concentration, and they're the ones that contribute most. These are the big three. If I added all the other ions and I did this equation and I did the other equation, the difference is so small that it really doesn't matter at a physiologic level. For a chemist, it may matter. For a physicist, it may matter. For a mathematician, it may matter. But at a physiologic level, it really doesn't matter. So you only need the big three. You only need the big three. This one has the largest effect on changing the membrane potential. This one has the largest effect on creating the membrane potential. And then chloride is always connected to these two and is a stabilizer usually. So with those three, you get a pretty good approximation of reality. You don't need to put every one of them in there. You just don't. Could you? Sure. You could do it. Add magnesium, add every other bicarbonate, add phosphorus in there. Everything that's got a charge on it. Just stick it in there, right? You could do it. It'd make it longer. It's not necessarily more difficult. Just taking more time to calculate. And then the number you'd get would be, you're looking at it, you'd say, I'm a practical person. You'd be like, why did I spend all that time doing this when the difference is, physiologically, it doesn't matter. Right? That's why. So this is Goldman-Hodgkin CAS. Okay? So this one is the one that calculates the resting membrane potential. So if I give you information about permeability, and you have information about concentrations, you could calculate this. It's not that hard. Again, if you guys have all done this at some point, right? These are not like blow your mind types of equations. And we're not running calculus here, right? We're not running rocket science. This is basic science, easy peasy. You can add, subtract, divide, press log on your calculator. If you don't know how to press it, I'll show you. Have you seen those commercials with the taxes? You know, they have those tax commercials where they bring in the Nobel laureate because he or she's really, really smart. And then they ask him what to do, and it's like, yeah, press that button. That would be me. I'll come in, you show me your calculator, and I'll tell you the same thing. Yeah, press that button. And if that makes you happy, I can do that. Okay. Questions on this? Yeah.
Really quick, what does the P stand for again?
Permeability.
Okay.
So remember when we went over that chart, partitioning coefficient, permeabilities, we did it for penetrating substances, right? But every ion, every non-penetrating substance also has a permeability. And that number is based on the channels, the open, closed, right? So every substance has a permeability. That's what that stands for. So I would have to provide you with the permeability. You don't know that. Right? I'm not asking you to memorize permeabilities of every substance we can use. I would have to, if I want you to calculate it, I would have to give you the permeabilities. Or else you can't do it. Or else you'd have to say, I can't do it because I don't know what the permeabilities are, even if you know what these numbers are. Okay, what do you want? Smarties? Lollipop?
What are Smarties?
Smarties. Good. All right. It's okay? Everybody gets that, at least initially? Okay, so that it's in your book, but it's not on my PowerPoints. I noticed it yesterday when I was looking through it. I thought, I definitely need to talk about this. All right. All right, let's connect up here, and we'll continue on where we were. Laptop. If somebody would douse the lights a little bit, I would appreciate it. Okay. Okay, autonomic nervous system. Okay, so let's go, not autonomic yet. No, sorry. I don't know how we got that far. We weren't that far. We were not that far. Oh, it's a big section, right? There's a lot of stuff to know. Okay, we were talking about No. Sorry. I don't know what happened. Somebody must have. One of my kids must have pushed the button. Okay, naturals. Alright, we talked about this, right? So, again, a lot of this stuff is in there for you. I'm not going to read it unless I think I need to explain something further. Remember that the sodium-potassium ATPase is electrogenic, meaning it not only establishes the sodium and the potassium concentrations, which are used as potential energy for secondary active transport, but it also makes the resting membrane potential, this thing, 3 millivolts more negative than it would be if it didn't exist. So it's called electrogenic. All right. Everything on here we already talked about. Okay. We looked at these pumps, right? So establishing the resting membrane potential. Here are sodium channels, which are normally closed. Here are some potassium channels. There are leaky sodium channels in some places in the body. We're going to learn about the heart, and that's where they exist. They're called F-type sodium channels, okay? But most of the body doesn't have leaky sodium channels for a good reason. But there are leaky potassium channels throughout the body. So there are types of channels that constantly leak a low level of potassium. What effect does that have on any cell if it's constantly leaking some potassium, assuming that there's no compensation? So if you're leaking potassium out of the cell all day long, a little bit, what effect does that have on the cell? Yeah. It makes it more negative. That's right. Now, it's compensated for by the sodium-potassium ATPase, right, and some other pumps. Getting back to what Alex said, the question he thought I was asking, the answer is, if I open up a bunch of sodium channels on a neuron or a muscle cell, right, and the resting membrane potential, let's say it's negative 60 for that muscle cell or neuron, and then I open up a bunch of sodium channels, what's going to happen to that membrane potential? Let's say it's negative 60, which is a big number. What's going to happen to that membrane potential when I open up those sodium channels? Now you have to know a couple of things. Where's the electrochemical gradient going? That's the first thing, right? If you don't know that, then you might get it wrong for the wrong reasons. What's going to happen to the rest of the membrane potential? What do you think? Yes. Okay, let me ask you a different question. Which direction is the sodium going to move when I open up those sodium channels? Into or out of the cell? Into the cell, right, because it's going down its electrochemical gradient. Okay, so it's going into the cell. So now let me ask my first question again. What is going to happen to the resting membrane potential of the cell when those sodium ions come into the cell? Josiah.
It'll become more positive.
It'll become more positive, right? Okay? It will start to depolarize. That's the term used. Right? It will depolarize. It will start to become less negative and more positive. Now, what's ultimately going to happen is if it's a cell, like a neuron or a gland cell or a muscle cell that can actually conduct an action potential, it will get to something called a threshold and then it will fire. Okay? But there's different ways for that to happen. So you're going to depolarize it, meaning you're going to make it less negative and more positive. Okay. Some of the terminology, RMP stands for resting membrane potential. Hyperpolarization, we'll talk about that. Hyperpolarization is when you go below resting membrane potential. So if my resting membrane potential for a theoretical cell is negative 40, then give me a value that would say that this cell is hyperpolarized. If my resting membrane potential is negative 40 at rest, and I hyperpolarize the cell, okay? You read the definition here. Give me a value that would suggest that this thing is now hyperpolarized. It's hyperpolarized. Yep. Negative 41 to infinity. Negative. Yes. That's right. That's what hyperpolarization means. Okay? Depolarization is going in the other direction. So when you hyperpolarize a cell, you're taking it further away from its resting membrane potential, usually in the negative direction. That means it makes it more difficult for that cell to be activated. That's what that means. Okay. All right, so if you look at this graph, this explains a lot of it, right? So if the hypothetical resting membrane potential for a cell here, it's always in millivolts. Remember, we don't do voltage in the body because it's too big. We don't do that. Is negative 70 millivolts, okay? If we depolarize it, it's going in this direction. So it's becoming more positive up to about 0. If you go above 0, it's an overshoot. So one of the very first things I told you about physiology when we talk about homeostasis is what? How we can correct things, right? Homeostasis is about correcting imbalances. But how quickly and how accurately does the correction get made? Remember what I said? Yeah. Could be 3 to 4 days. That's sodium, right? But what about other things that happen on a faster scale? When we did the insulin, remember the insulin response or the glucose response? What did we see there? How long did it take for it to get back to baseline? Remember, give or take, just ballpark. A couple hours, right? But did it go back to where it started right away? Do you remember that graph? No, it doesn't. It actually does a little bit of an overshoot in the negative. So if your resting blood glucose level was 60 milligrams per deciliter, which is kind of low, let's say 70 milligrams per deciliter, you may shoot down to about 68 and then tweak it back up. So when physiologic systems are fixing things, they usually overshoot or undershoot just a tad. The bigger the insult, usually the bigger the overshoot and the undershoot, right, in the correction. Does that make sense? The bigger the insult to whatever the system is, the more likely when it goes to correct it, it's going to overcorrect. Think about the first time you ever threw a ball, okay, and you're targeting. So I'm always amazed at how, as I'm thinking about sports and human physiology and anatomy all the time, is how accurate an NFL quarterback can be. Think about it, how far down the line these guys can throw this ball. Not only can they throw it, but how accurately. Like, they put it in, and you've all seen this if you ever watch football, right? But they can put a ball in a place where nobody else can touch that ball except for the guy on their team that needs to touch that ball. All right? Think about how that system, the vestibular system that's involved in all this coordination with your cerebellum, all the stuff that's going on, and all of the calculations that your brain has to do in order to make that happen. Everybody know what a wheel kick is in soccer? Right? That's where you kick the ball and you then go up and over and back. Right? It's really impressive. If you've ever seen sports science on ESPN, they've done the calculation for how accurate you have to be to pull that off. You have like 1/10 of a second in either direction to be able to do something like that, to make it even happen. And people can do it, right? So, but there's still a little bit of an overshoot or undershoot. But when they were trying to learn all of that, it was ugly, right? Like sometimes it'd be way over in this direction. They throw the ball and it's way over their head. Sometimes they would throw it and they would undershoot in the other direction. It's way short, right? And so after a while, as you do this more and more, as the system becomes better, those overshoots become smaller and undershoots become smaller and smaller. Okay? So that's a large, long period of time. But the body can do this all the time, and there's usually an overshoot or an undershoot. It's not perfect. Physiology is ugly. Right? It is not perfect. It's not like a chemistry experiment. Okay, you have repolarizing. We're going to talk about repolarizing this. Repolarizing essentially is once something is depolarized, it's been activated, right? You can think about depolarizing as activating a cell. To bring it back to resting membrane potential is called repolarizing. And then if you go beyond, you overcorrect in this case. You're going to hyperpolarize the cell. That's useful. And so sometimes when this happens in physiological systems, there's actually a good reason for it to happen. It's not just a mistake. Okay? So these are terms you need to know. This is activating. This is you've activated it too much. This is you're bringing it back to resting. This is you're overshooting that correction. And then this is the resting membrane potential. What we don't have here is something called a threshold line. And this would be the amount of depolarization that needs to occur before a neuron or a muscle cell becomes activated. Because you can get almost there and not actually activate this thing. Okay, we're going to talk about that too. So any questions on this? So this is sort of a nice, easy graph so you can understand these complex issues. Okay. So we're going to talk first about a type of depolarization. Okay? A type of depolarization where sometimes called end-plate potentials. Sometimes they are called end-plate potentials, and let me give you some other names that they go by. Graded potentials. Graded potentials is the more basic general term. Okay? What does that mean? You have a cell. Okay, you have a cell, and this is a channel. Let's say that this is a sodium channel. It doesn't matter what the resting membrane potential is of this cell. It's probably a neuron. Okay, it's probably a neuron, but it doesn't have to be. Okay, and what ends up happening is you open up one of these channels. Let's say it's sodium. So which direction is the sodium going to go in or out of the cell? Into the cell. And what happens is you bring in these positives, and what is it going to do to that resting membrane potential? Let's say it started at -70. It's going to make it a little bit more positive. Okay. Now, not in all cells, but in some cells, that may change the resting membrane potential a little bit. Now, because you've only opened up one channel here, notice what happens to that resting membrane potential. So let's say it went from -70 to -68 because of this one channel. Use exact numbers, okay? And that happens right here. Now what happens when you go from this side to this side, or this side to this side? There's a hint there, right? What happens to the positive charge? What happens to that circle as you move further away? Somebody else? I heard it. It decreases in size. That's right. So if this is -68, let's just use exact numbers. Let's say that this is now -69, and it's -69 here. Okay? Everybody with me? What happens when you get outside of this box area here? Take a guess as to what the membrane potential is outside of this area. -70. That's right. It's the same. Have you changed the membrane potential a tad? Yes. Is that enough to cause what's called an action potential? An action potential in a muscle or a neuron is what's called all or none. Either it happens or it doesn't. A graded potential is not all or none. This enables cells to tweak up or down. They're tweaking potential, if you want to think about it that way. Okay. Could a graded potential cause an action potential? Yes. If you get enough of them together. Okay. So if you look at it here, right, you have the site of the initial depolarization being in the middle. As you go further and further away, what happens to the resting membrane potential? Or the depolarization, it decreases. Okay, so huge difference between a graded potential and an action potential is that a graded potential is decrementing, meaning it decreases its intensity with distance. An action potential does not. If an action potential fires with a neuron, it goes, and it doesn't decrease in speed, and it doesn't decrease in intensity. But a graded potential does. They're very, very different. Right? One is to turn muscles and neurons on and go. It's like go. There is no thinking about it. The other one is tweaking a system. All right? You may want to get to an action potential, but you may not. There's a lot of little things that go on in the physiology all the time, sort of to tweak things up or down, and there are good reasons to do that. Graded potentials are used for that. Action potential, once you've started one, you can't stop it. It's like a nuclear reaction, right? Once you start it, very, very difficult or impossible to stop. So, good or bad, it's going to happen now. You can't do anything about it. That's a huge difference you have to understand between these two. And there are different kinds of graded potentials. Everybody get this. So here you have a ligand, right? So this is a ligand-gated channel that caused this. Question? Graded potential. So talk a little bit about graded potentials. So graded potentials are changes in membrane potential that are confined to a relatively small region of the plasma membrane. Okay? They call graded potential simply because the magnitude of the potential change can vary. And it's usually small. Graded potentials are given various names related to the location of the potential. For instance, the receptor potential, synaptic potential, pacemaker potential. We're going to see all of those. When we get to skeletal muscle with the neuromuscular junction, that is a graded potential that occurs there between the motor neuron and the muscle cell that's called an end plate potential. It is another type of graded potential. It has a special name. That's all it is. So once you know what a graded potential is, you're like, well, these are just different versions of that. They are just specific names for specific areas. Like a pacemaker potential, when we get to the heart, the reason your heart beats at whatever if we took your pulse right now, let's say your pulse comes out to be 55, right? That means that your pacemaker potential for your heart is set at roughly 55 beats per minute. That's all that is a graded potential. It's called a pacemaker potential. It's in your heart. That's why your heart has a pacemaker. If anybody here has a grandparent, an old relative who's had to have an artificial pacemaker put in, all it is replacing the natural pacemaker, which isn't working anymore. It's a graded potential, but the one they put in is an electronic, mechanical graded potential maker. It's a piece of metal that generates an electrical current, and it keeps their heart beating. That's all it is. We've had it for 50 years, right? It's not really like high technology. It isn't, but it essentially does what the body does naturally. Okay. Examples of these graded potentials, right? So you can have a graded potential that's depolarizing, but you can also have a graded potential that's hyperpolarizing. Because there are neurons that are excitatory neurons, and there are neurons that are inhibitory neurons. And they tweak systems. Okay? A motor neuron, the one that would cause my muscle to do this, once I turn it on, it's on. That's it. Once I fire a bunch, it's just going to, my bicep is going to flex. There's no in between. It doesn't sort of flex. Right? It either does. Now, the strength is more complicated, but it needs either on or off. This is not. So, motor neuron, when you turn it on, it can only have an active potential. But what comes into that motor neuron can tweak it up or down. All right. If you have a weak stimulus or a strong stimulus, okay, in PhysioX, you do an experiment that works on stuff like this. Right? It's very, very good. You actually get to see this happen in real time. And it's kind of cool. So that's why those PhysioX exercises are super important, because it's okay. They're super important. They're super important because that you can actually see what I'm talking about. You're like, oh yeah, we did that experiment. I saw that happen over and over again. That's the way it works. Versus seeing a still. Right? So you can have a weak graded potential or a strong graded potential. You can measure it at the site of the stimulus, and you can measure it at 1 millimeter away. So what does this one show? What happens to the strength of the graded potential as you move further away from the site of which it was originated at? It decreases. And that's for either the negative or the positive, right? It doesn't matter which direction it does. Everybody good with that? Yeah. All right. An action potential. So I'm going to talk about action potential. I'll just read this one. I don't like reading slides necessarily, but I think for this one, we're going to slow me down a little bit, so I'll read it while you sort of take this in. Action potentials are generally very rapid, as brief as 1 to 4 milliseconds. Right? Milliseconds. 1 to 4 1,000ths of a second. That's pretty darn fast. Right? You can't even conceive what that is. Maybe talk about it, but you really can't conceive that speed. Right? And may repeat at frequencies of several hundred per second, which is a little slower. Okay. The ability to generate action potentials is known as excitability. There are very few cells in the body that have this capability. Muscle, nervous, neurons, and then there are some GI, and then there are some glandular cells that have this capability. But for the most part, it's mostly muscles and neurons that have it. So if that's all you remember from this class, good enough. An action potential is a large change in membrane potential and is an all or none response. If you have an action potential, there is none of this. It doesn't look like this at all. Okay, these are graded potentials. So let me draw you what an action potential would look like. And I'm going to put in threshold. So if I'm not drawing this big enough, let me know. All right? So this is time in milliseconds because this is fast. Right? This is the resting membrane potential in millivolts. Let's take a neuron that's resting membrane potential is negative 70 millivolts. And let's say that at negative 55 millivolts, we'll say this is 0. We'll say this is plus 20. Right? So its resting membrane potential is negative 70. If you're going to have an action potential, you have to have a threshold. This is threshold. Okay? So what can happen is maybe you can have graded potentials that sort of do this to the resting membrane potential. They depolarize it. As soon as it gets to the threshold, you see this. It's hard to understand how fast that really is, right? But not that I did it quickly, but what's going on here, right? That's what an action potential looks like. It's massive. It's a spike. And so, right, you're depolarizing the cell here, right? And most of the time when we're talking about neurons, the depolarization is caused by sodium into the cell, and the repolarizing, right, sodium in is potassium out. And then this is hyperpolarizing here, right? So that's hyperpolarizing. That's what an action potential looks like. A graded potential looked like this. Maybe even like this. Or like this. Right? These are graded potentials. That's an action potential. And it's got an overshoot built in, right? Because this thing is so powerful that it overshoots by a lot. 20 millivolts into the positive range. But this happens in hundreds and thousands of a second. That's how fast this process is. This is not happening at that rate, and it's not that large. So that's the major difference between the two. Questions? All right. So this just looks at channels, right? You have to remember that the sodium channels have 3 states: closed, open, and inactivated. Potassium channels only have 2. Okay. You can read this. The high point here, the most important thing for me to explain to you, you can read the rest of it, is this is actually the membrane potential. That's essentially what I just drew here. Okay, membrane potential, here's threshold, it goes up, goes out, it hyperpolarizes, it comes back. This is showing you what is happening to the sodium channels along the way and what is happening to the potassium channels along the way. So the sodium channels open up about here, okay, about here, and the potassium channels open up about here. Okay, so what does the PNA and the PK mean? This is showing you what happens to the permeability of each of those ions during that entire process. So when is the permeability to sodium highest? Near the beginning of the action potential or the end? Where is the permeability of the sodium ion highest? Near the beginning or the end? it's near the beginning, right? As soon as you get to threshold, but this is where it peaks. So right here, you have as much sodium coming into that cell and as many channels open as you possibly can. So it's permeable because the channels are open. So this is essentially, most of the channels are open over here. Actually, it's actually, there's a delay built in. The delay, the channels are probably maximally open here, and you can get a delay effect. But, okay, same thing with potassium. When do you want the potassium permeability to be higher? Near the beginning of the action potential or at the end of the action potential? According to these graphs, the red. At the end. Right, because I told you that sodium depolarizes cells, potassium repolarizes them. And this is the proof. You can actually look at the channels and see when they're open and closed and say, okay, that sort of makes sense. Right? So if I ask you something about permeability, this is what I'm referring to, this graph with these two curves on it. And just know that, well, at the beginning of this thing, near the beginning, the first half is when a lot of sodium is coming in, lots of channels open, and toward the second half is when a lot of potassium channels are open. Potassium is leaving. And that's how we get this curve. So that these two come together to form this. This is measured in millivolts. This is looking at membrane permeability, which is a number that really doesn't matter. Okay, you can read through. It may confuse you. Yeah.
Do the potassium channels close when the sodium channels open? And vice versa?
Usually, there's a delay effect, right? So the Ariel said, right? Yeah. Her question is, do the potassium channels open when the sodium channels close? In fact, in this case, it's in an inactive state. It's not actually closed. So, and that means something, because that inactivity, we're going to talk about how you can sort of juice the system to get this ball to come out of here, which is kind of cool. But generally, yeah, as one is turning on, the other one is turning off. You generally don't want them simultaneously active. Although when we get to the heart, I'm actually going to show you an example where you have multiple channels open at the same time and they're going in different directions. But there's a utility to that. But in a neuron and in skeletal muscle, generally they're not open at the same time, and if they are, it's for a split second. Okay? Good. You like lollipops?
Sure.
Okay. You want the last lollipop? You already have this again. All right. Which flavor do you want? There you go. Okay. Question. Yeah.
So do you ever see a cell getting more positive than around plus 30 millivolts? Assuming that's
Oh yeah.
the most.
Oh yeah. Yeah. I mean, but generally no. I mean, but you could see it. There's always exceptions to rules. Yeah. In other words, can a cell, when it depolarizes and overshoots, can it go above plus 30? Sure. Sure. It's a rare beast.
I mean, if that's the most, the cell can be open, how do you get more positive?
How does it get more positive? But why would you want to get? Why would you want to make it more positive than this?
Just wondering, can.
You can, but there's no reason to. Okay. So Michael's question is, can you make the cell more positive than positive 30? You can, but you really don't need to, because this is an overshoot, right? You don't need to. There's really no function to this overshoot. It just happens, right? But you don't need to activate the cell. You don't need to make it more positive. Making it more positive could potentially have a function of slowing down the next firing, right? Because now you got to bring it. Because you can't fire another neuron, that same neuron in that same cell, until you can sort of. But for the most part, you have to wait until a certain level of repolarization occurs to fire another one. So the higher that goes up, the longer it's going to take it to come down, which means it's going to slow down. So when you're doing something, if you're an athlete, right, let's say you're on the track and you're running a race. Let's say you're running a 100-meter dash, right? You're running a 100-meter sprint. I mean, this on-off thing is going at a pretty high rate, right? And so if the overshoot was even greater, it would actually physically slow you down. You couldn't turn your legs over faster. It would be slower. Yeah.
That's like a comfort, backward, forward,
Yeah, so there's fast and slow twitch muscles. That's sort of nuance here, but they're different, right? But yes, There are differences, but so there are certain types of muscles that can fire faster and stronger than others. But that being said, as a general principle, the overshoot principle is still the same. Whether you're using fast or slow twitch, the bigger the overshoot, the longer it takes you to repolarize. Yeah.
Yeah, the question is like, if you make it more positive or more negative, then you can affect the rate of.
Yes, yes. So the bigger the overshoot or the undershoot, you will start affecting the rate. That's right. And that's why it's not more isn't always better. That's exactly right. Right? Because the body then has, the bigger the overshoot, the bigger the insult, the more energy you gotta pull. Think about that. If you're running, right, if you're doing one of these, to stop yourself, right, I'm not sure why you want to do that. Walking is much easier and it looks much better, but let's say you want to. I saw some guy yesterday, almost hit him. Old guy. He's going to. Right? I'm pretty sure I can walk faster. He can walk faster. Anyway, so use that as an example, right? You have some guy doing that, and then you have some person who's like running as fast as they can. Which one is going to be easier to slow down, stop, and or reverse that action? The guy that's doing this, or the guy that's like that? Think about it. Which one is easier to slow down? Have you ever seen what happens at the end of the gold medal race for the 100-meter dash in the Olympics? Do they just stop on a dime? Has anybody run this race or has run this race? You're going as fast as you can. You can't slow down. Has anybody ever seen the video of Bo Jackson scoring a touchdown and going through the stadium through the doors because he couldn't slow down? He actually opened up a door. Or else he would have gone into the wall. So he pushed the door open and just kept going. It's hysterical, right? So it's pretty funny. It actually is when we play with Raiders. Same thing. Can you slow down? You can't. You try. It's the hardest. It's actually harder to slow down than it is to accelerate sometimes, right? So this is the same thing here. When you have a bigger overshoot or undershoot, it's just harder to do. It takes more energy, right? It takes more energy. So same idea. Okay. So this is a nice schematic here that sort of gives you an idea of what's happening, this negative feedback loop when you have an action potential occur. Right? You have a depolarizing stimulus. It opens up these what are called voltage-gated sodium channels, which means that they're millivoltage sensors on them. They have a volt. Remember how I drew you the voltmeter? These channels actually have a built-in voltmeter. You know, it's a little machine that they put in there when you're born. God puts it in there, and and he tweaks the voltmeter, and then he's got a bunch of angels that go in there, and then they tweak it, and they test everything to make sure that you're fine, and there's the voltmeter. And it's really, really small. Not really. But it's sort of like that, right? But there is a sensor in there, and it's like a voltmeter. Okay? And then what happens is that you increase the permeability. When it gets to a certain millivoltage reading, the channels opening increase the permeability, right? Because sodium won't just come through the plasma membrane. And you have an increased flow of sodium into the cell, and then you depolarize the membrane, all right? And this can continue. Or you can have an inactivation of sodium channels, right? Depending on if the stimulus stays, let's say I bring in an electrical stimulator and I attach it to somebody. I'm going to hook Dominic up. I'm going to put it on his leg. All right? And then I'm going to put Alex in front of him. So I'm going to stick it on this muscle right here, and I'm going to stick Alex in front of him. I'm going to turn it on. Okay? And I'm going to stick a couple of them here and here and here. I'm going to turn the electrical stimulator on. What's Dominic going to do to Alex? He's going to kick him where? Alex just turns and Alex is facing this way. You're going to kick him in the butt, right? So if I continue to keep that electrical stimulator on, Dominic's going to keep kicking Alex in the butt. Alex is going to get mad, right? Because if somebody kept kicking you in the butt, you'd get mad too, right? But if I shut the electrical stimulator off, then Dominic will stop kicking him in the butt. He won't get mad, and they'll still be friends. Okay? So if I shut it off, then it's going to be inactivated. The potassium channels do the same thing except in a different order, right? So towards the end of this thing, right, towards the end of this process, you open voltage-gated potassium channels, They increase their permeability, right? Because as they're open, that means more potassium is leaving the cell. And then you increase the outflow, and then you have repolarization. So this is essentially what we've seen here and here. It's just another format. So whichever format you get, remember that one. We have 3 versions, same story. Okay. Clinical effects. Xylocaine and Novocaine. Xylocaine and Novocaine, how they work, right? These are pain, they numb you. Right? How do they work? Well, the generation of action potentials is prevented by local anesthetics. Okay? Because the drugs block a voltage-gated sodium channels. So now the next time a doctor, a nurse, or a PA, somebody gives you Xylocaine, or Novocaine, or Procaine, you're like, voltage-activated sodium channels. And they'll look at you and go, huh? What are you talking about? Don't worry about it, I'm just taking physiology. Alright, without action potentials, graded signals generated in the periphery in response to injury, for example, cannot reach the brain and give rise to sensation. There is a naturally occurring sodium channel antagonist. It's called tetrodotoxin. And it's made by an animal called the pufferfish. We used to have one in the lab, 218. You may have never seen it. In the old Anat-Phys lab, there was a pufferfish, and it was puffed up, and it's got spines on it, and it's about this big, and it looks like it's a balloon. It is a real fish. They exist. South China Sea, Japan area, right? And it is lethal. And if you get stung by one of those spines, the tetrodotoxin is so potent that it will shut down all of your voltage-gated sodium channels. How does it kill you? You can't breathe anymore. Because your diaphragm muscle works the same way as your other muscles. You can't fire an action potential. You can't breathe. If you can't breathe, you're going to die. There are crazy people. I will end on this. Crazy. Insane, in my opinion. Take it for what it's worth. In Japan, eating a pufferfish is a delicacy. So you have to be a chef that's trained for I don't know, umpteen years to be able to. You've got to be able to bring in the pufferfish, know how to handle the pufferfish, take out the glands, right? And then people eat this. They know going in that this thing produces a poison that could kill them, and yet they eat it. And so most people, if you've ever done this, talk to people who do this, their tongue and their lips are numb for about a day after they do this. And that's because the chef that prepared this is fantastic. If you get the Schlepp chef, the guy that walked in, and he's got boogers hanging out, and he's sort of all disheveled, and he prepared this thing, and his name's Bob, that prepares this. If you're eating pufferfish, and the chef that prepared his name is Bob, walk out there. Pretty sure you don't want to have it prepared by name. If you can't pronounce the name, and it sounds like Chinese or Korean, then you're probably okay. Probably okay. And he's old. He's young, stay away. Don't eat pufferfish. Okay. Question. That's my pufferfish story. All right. Any questions? All right, so Friday. Quizzy poo. Right? Questions? That's pretty good. I only got one left, so. All right. Have a fantastic day. Yes, ma'am. How do other fish? You mean the fish that eat it, or the fish? Oh, it'll. That's how it kills things. Oh yeah. Oh yeah. And it protects itself. That's how it protects itself.
We used to have a pufferfish. My dad would have to eat him cautious.
Oh yeah. Now, how much of it you have to be injected with that? It's not the most lethal toxin in the world, but it's pretty lethal. And actually using it in neuroscience experiments. The lab I used to, that postdoc in, I never touched it. But yeah, so it's protection. And so other fish, potential predators, no. That's why when it pops up.
Because they do that in response to things.
Yeah, that's right. It gets scared and it pops up. And then any fish that's smart enough to say, yeah. Now, there are animals that are immune to tetrodotoxin. That's Yes, sir.
So, I went to Friday for test.
Yep, I got the.
The email?
Yep.
Great. So, maybe Monday after class? Quiz?
Hold on one second. I'm just trying to. I don't want to. I don't want the details. Save. Nervous one. Okay. That's not the one I wanted, though.